This one is by Siyi Gong, where she'll be talking about joint commitment in human cooperative hunting through an imaginative we.
Hi everyone, today I'm going to present our study on sharing intentionality and cooperation. Cooperation is heavily grounded in vision. Even young toddlers can use their shared vision environment to coordinate cooperation. One specific aspect of this cooperation is that they're willing to commit to achieving a shared goal together with other collaborators. Examples include they will protest when partners disengage, and they will continue to collaborate even after receiving the reward prematurely. This is remarkable, especially considering toddlers don't even possess a mature system for explicit communication. They mainly rely on bodily movement and visual scenes for context. However, animals, to our knowledge, do not show such level of commitment to collaborative activities. Developmental work reveals this uniquely commitment-oriented cooperation in human is rooted in the mental representation of shared intentionality or individuals as a group. Joint commitment through shared intentionality acts to forcefully regulate a team, especially when there are high temptation for individuals and when the task is difficult. Inspired this concept, we propose that joint commitment is achieved by individuals' mental representation of an imagined super agent. So instead of having a realistic set of individuals, each thinking about what I want to do and what you want to do, individuals imagine a we agent that stands as a super agent with its own mind, taking a bird-eye perspective over all agents and directly control the agent's action. So each of them would be thinking a question, what does we as a group want to do? In our study, we first asked the question, do humans commit to shared intention when they cooperate? If they do, theoretically, they should be able to commit to a shared goal even without explicit communication in a collaborative hunting task, which requires complex coordination and marks the first unique cooperative activity in humans' evolutionary history. We empirically tested this in a real-time simulated physical engine. In our cooperative hunting task, there are 3 hunters and a varying amount of prey. The hunters are controlled by human participants who are not allowed to verbally communicate with each other. Hunters aim to catch the prey, while the prey aims to avoid getting caught. Crucially, there are 2 types of reward defined by the duration of contact between a hunter and prey. A touch is defined by 0.05 seconds of contact and will bring a joint reward of 0.1 to the group. On the other hand, a catch is a more stringent contact defined by 0.3 seconds by any hunter with the prey and will bring a reward as high as 3 to the group, which is more motivating to the hunters. Because catch requires higher quality of cooperation, we focus on this analysis later. We further manipulate temptation to individuals by varying the amount of prey. While there are always 3 hunters in the display, there can be 1, 2, or 4 prey. We also manipulate the difficulty of the task by varying the maximum speed of the prey, which can be 0.7, 1.1, or 1.5 times speed. What we want to see is if humans can handle the challenges through joint commitment by collectively identifying one prey among others and persistently pursue that prey without any team member getting distracted by other hunting opportunities. Here are a quick demo showing how human hunts in 4 targets condition. As you see, the hunters in red, blue, and green do not have a clear shared goal in the beginning. However, they gradually converge onto one goal and focus on that prey and never let it go afterwards. Now that we get a sense of how humans hunt, let's take a look at the actual data. Here the x-axis indicates different speed and bars of different colors indicate different set size, and the y-axis represents accumulated reward from both touch and catch. We see that for 0.7 speed, human accumulated reward does not drop as the number of prey increase from 1 to 4. Although their average performance dropped as speed increased, which is not too surprising, but with the more challenging speed, the performance still maintained with larger sparse size. We see from this data that human can form joint attention to avoid being distracted by large amount of potential targets. So the answer to our first question is yes, humans do commit to shared intention in collective hunting. But the next step, we want to know how can we computationally model shared intentionality, allowing it to measure up to human benchmark performance in the same task. Our model is inspired by previous modeling work using a Bayesian theory of mind approach in multi-agent setting. We're interested in modeling a joint commitment through a shared agency account by using continuous stream of visual information and presenting challenges of several alternative targets. The idea is that when agents jointly commit to a shared goal, they mentally form a single autonomous we agent with its goal that was believed to rationally control an agent's action. The challenge with this approach is that this we agent is not real. Each agent makes their own version of we, and naturally, they can think of a different goal for their own we agent. So the question is, how can different versions of we converge with each other based on vision alone without communication? We approach the question with a three-step process. First, each agent samples a joint goal from the respective distribution of the super agent's intention. This is the goal sampling phase. Then, given a joint goal, the agent samples a set of joint action by simulating a centralized planner. This includes their own action and the expectation of the other agent's action. This is the planning joint action phase. Once each agent has conducted action to the environment, their states are being updated. By observing the world and what the others has done, each agent inferred an updated we mind that better explained other hunters' movement. This process then repeats itself as the time step updates. Essentially, each agent infers what we want to do by looking at what we has done. And through this repeated updating process, we expect agents to have increasingly similar belief distribution about their own we agents. In the demo that I'm about to show you, the accumulation of agents' inferred joint goal on a single prey is reflected by a change of prey's brightness. Dark color will represent no convergence, whereas bright yellow color represents convergence of beliefs. As we can see, at the beginning, different agents have very different ideas about what we want. Gradually, some targets become brighter. And boom, eventually one target gets the brightest, indicating what agents we converge on the target. As a baseline, we also employed a state-of-the-art model from OpenAI that combined reinforcement learning with deep learning on multi-agent coordination. In this model, cooperation is encouraged by assigning the same reward function to all agents, thus effectively allowing agents to share the group reward, so we call the reward sharing model, or RS model for short. There is no representation of intention where the hope is that the shared reward itself alone is enough to handle cooperation. And thus, RS model fundamentally diverge from developmental theories. As you can see from this demo, the RS model is pretty powerful when there is a single prey in the environment, even when there are obstacles. But is it powerful enough to keep a team together with their multiple goals? When there are 4 prey in the environment, we see that RS teaming seems pretty paralyzed. Each agent is busy going after a different prey and easily switch target when new opportunities show up. They never really commit to a shared goal. Now let's look at some data. Compared to the previous human data that we've seen, for 0.7 speed, the human IW model's performance does not drop as the number of prey increase, whereas the performance for RS model dropped as the prey increased from 1 to 4. All agent performance dropped as speed increased, but even with faster speed, the performance across set size was maintained in IW model but not RS model, whose performance drastically dropped with more prey in environment. Now we focus on the high quality catch data. We see similar patterns in catch data where number of catches are maintained across set size in humans and IW model, but not the RS model. Collectively, these results really show us how RS performance is easily impacted by more prey environment, but not IW, who has a representation of joint commitment through shared intentionality. In addition, we also want to explore when the hunting is judged by a third-person perspective, how our successful catches get attributed to teams' collective effort as opposed to individual efforts. Therefore, we recruited new participants who watched a catch video compiled from experiment 1 from all types of agents, and they're asked to rate the contribution of each hunter in the video. If the catches are judged to truly result from cooperative efforts, all agents in a team should have similar rating, resulting in a small contribution range. If not, then some agents should get high credit, while the others get low credit, resulting in a large contribution range. Here we have the x-axis represent number of prey, and the y-axis represent contribution range for each type of agent. As we can see, for all set size, the contribution range for humans and IW are consistently low, whereas the contribution range for RS team, when the numbers of prey increase dramatically, indicating that even the catches in RS trials are not due to equal contribution from all hunters. So the answer to our second question is, yes, we can capture the complexity in human performance by building a joint commitment model by sharing intentionality. But so far, all models have the same base algorithm, and it's easier for them to cooperate with their own kind. The third question we have in mind is, how do the models cooperate with humans? Can it develop hunting strategies compatible with human and achieve seamless cooperation? We designed post-hoc teams consisting of humans and models. For each of the 3 hunters, we sample one agent from the agent pool of humans, IW models, and RS models, and let them do the hunting task, making a total of 6 possible combinations. Here's a demo of a human cooperative with IW model. So without me telling you, can you see which one is the IW model and which 2 are the human hunters? It's pretty hard, right? So the IW hunter is actually in blue, but this really gives you a sense of how well IW hunting is competitive with that of humans. For the next few graphs, the x-axis will be the set size, and within each set size, bars of different colors represent a type of team, and the y-axis is the cumulative reward of a particular type of team. On the left side, we have team consists of humans, IW. On the right side, we have team consists of human, RS. We can see that when there are 1 prey, all types of team perform equally well. However, when prey increases to 2, the performance maintained with addition of IW hunter in a team, but the hybrid team kind of suffer from the addition of RS hunters in the team. We even see more dramatic patterns for 4 prey, where the lack of commitment in RS hunters' hunting strategy is more evident with more individual opportunities. So the answer to our last question is, yes, IW model can seamlessly cooperate with humans, but not so much with RS model. In conclusion, our study found that humans can achieve visually grounded commitment without communication. IW model with stronger constraint of joint commitment resembles human level performance and cooperates with humans smoothly. Lastly, RS without a strong constraint on cooperation cannot cooperate robustly in challenging scenarios. In summary, our work turns developmental theories on shared intentionality and joint commitment into workable frameworks and tested it in online multiplayer psychophysics task. We then build computational model based on the framework that can seamlessly cooperate with humans. Our study also shows that vision is not only about individual perception of object and scenes, it's also the cornerstone of human unique cooperation. Special thanks to my supervisor, Tao Gao from UCLA, the first author, Ning Tang, and collaborators from UCLA Psychology Department at Zhejiang University. Lastly, I just want to say, Ning, the main author from our group, is going to give a poster on how vision supports understanding and visual social interaction, studying the combination of intuitive psychology and intuitive physics. And we would love to see some of you there. Thank you.
Yeah, this isn't working either. Okay. Oh, there you go. Yeah, no. Yeah, perfect. Yeah, sorry about the feedback. It's happening in both rooms. It seems, and outside too. It seems to be a fire alarm. Yeah, exactly. So hopefully it'll, yeah. Yeah, no, yeah, exactly. Yes, yeah. But hopefully it'll get fixed soon. But questions? Yeah, go for it.
There's a beautiful set of ideas. But I wonder if you've thought about the connection to what are called coordination games in economic game theory, and where, in effect, these kinds of problems can be solved with absolutely no prior coordination and no prior communication. They're sometimes called focal point tasks, and they were invented by the Nobelist Thomas Schelling. And it seemed to me that if we can agree on a prior strategy, it's nowhere near as interesting as if we can solve the problem with no prior strategy.
I think that's a really interesting idea. Thank you for bringing it up. I just thought that some of the strategies that we've seen in our human performance are not exactly, they might not be rational, but they are committed as a group. So I think it would be also very interesting to explore that idea in economics. Thank you for bringing it up. Yeah.
That's all the time left, unfortunately, we have for questions, but thank you. See you.